Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we will discuss crystal field theory applied to octahedral complexes. Let us see, first of all, what is crystal field theory. The crystal field theory was proposed originally for ionic crystals and not for complex compounds, and it was proposed by H. Bethe in 1929, and thereafter it was modified by J. Van Blake in 1932. Later on, this theory was applied to coordination compounds by Orgel in 1952, that is, after 20 years. Thereafter, this theory became very popular. This theory is nowadays widely used to explain the spectral as well as magnetic properties of the complexes. Please note that the crystal field theory was originally proposed for ionic crystals, and then it was applied to coordination compounds in 1952, and nowadays this theory is very popular in coordination chemistry, and it is used to explain the magnetic as well as spectral properties of the complexes. Now let us see the postulates, the assumptions of crystal field theory. A coordination compound is made up of a central metal ion, which is abbreviated as CMI, and it is surrounded by a number of negative ions or neutral molecules which are called ligands. Any complex compound is made up of a central metal ion which is surrounded by a number of negative ions or neutral molecules which are called ligands. The metal ligand bond in a coordination compound is purely electrostatic in nature. It means electrostatic attractive force acts between the central metal ion and the ligands of a coordination compound which binds them together. The main theme of CFT is that the metal ligand bond of a coordination compound is purely electrostatic, that is ionic in nature. There is no overlapping between the orbitals of central metal ion and the ligand, because if it happens, it will lead to covalent character in the metal ligand bond. But in the crystal field theory, it has been assumed that the metal ligand bond has 100% ionic character, and therefore there is no overlapping of orbitals between the CMI and ligands. The negatively charged ligands are treated as point charges. On the other hand, the neutral ligands are treated as point dipoles. Please note it again that the negatively charged ligands are treated as point charges, while the neutral ligands are treated as point dipoles. And let us now see the next assumption. During the formation of a complex compound, a certain number of ligands approach the CMI along certain directions with their negative end towards the CMI. It means during the formation of a complex compound, certain number of ligands approach the central metal ion along certain directions in such a way that their negative end is towards the CMI, and an electrostatic attractive force may act between the CMI and the ligand. The ligands produce negative electrostatic field around the CMI because their negative end is towards the CMI, and therefore the ligands overall produce a negative electrostatic field around the central metal ion. All the 5d atomic orbitals of the free metal ion have the same energy, that is are degenerate. In free transition metal ion, the 5d atomic orbitals present in the valence shell have the same energy, and thus they are degenerate. But when the transition metal ion forms complex compound, its d atomic orbitals remain no more degenerate. When a transition metal ion forms a complex compound, its d atomic orbital remain no more degenerate. That is, their energy differ. These d atomic orbitals are split up into two or more sets of orbital under the influence of negative electrostatic field exerted by the ligands depending upon the geometry of the complex. When a transition metal ion forms a complex compound, its d atomic orbital splits up into two or more sets of orbital under the influence of negative electrostatic field exerted by the ligand, and the mode of splitting of these d atomic orbitals depends upon the geometry of the complex. It is called crystal field splitting of d atomic orbitals of the central metal ion. And the eighth assumption is that the energy difference between the highest energy d atomic orbital and the lowest energy d atomic orbital of the central metal ion in a complex compound is called crystal field splitting energy. Let us see it again. The energy difference between the highest energy d atomic orbital and the lowest energy d atomic orbital of the CMI in a complex compound is called crystal field splitting energy, and it is denoted by delta with a suitable subscript. The splitting of d atomic orbitals of the central metal ion in a complex compound leads to decrease in the energy and increase in the stability of the system. It means when the d atomic orbitals of the CMI of a complex compound are splits up, it decreases the energy and increases the stability of the system, and this increase in stability is called crystal field stabilization energy, CFSE. The splitting of d atomic orbitals of the central metal ion leads to decrease in energy and increase in stability of the system, and it is known as crystal field stabilization energy. A splitting of d atomic orbitals of the central metal ion in the octahedral crystal field. During the formation of an octahedral complex, generally six monodentate ligands approach the central metal ion along the axis x minus x, y minus y, z and minus z as shown in the figure on the next slide. 5d atomic orbitals of the CMI have also been represented diagrammatically on the next slide. Let us see it again. During the formation of an octahedral complex, generally six monodentate ligands approach the central metal ion along the axis, two on the x-axis, two on the y-axis, and two on the z-axis. It is the diagrammatic representation. This is an octahedral complex COF6 triple minus. During the formation of this complex ion, six F minus ions approach CO triple plus ion, which is the central metal ion here, while F minus is ligand. Two F minus ions are on the x-axis. Two F minus ions are on the y-axis, while remaining two F minus ions are present on the z-axis. And these are 5d atomic orbitals of the central metal ion. DYZ has lobes between y and z axis. DXY orbital has lobes between x and y axis. DXZ atomic orbital has lobe between x and z axis. While it is obvious that these three d atomic orbitals, DYZ, DXY, and DXZ, have lobes in between the orbitals, in between the axes. That is, the lobes of these d atomic orbital are away from metal ligand direction because the ligands are present along the axis, while the lobe of these d atomic orbitals are in between the axes, and hence they are away from metal ligand direction. On the other hand, the lobes of dz square or atomic orbital lie on z-axis, and the lobes of dx square minus y square atomic orbital lie on x-axis and y-axis. The lobes of these two d atomic orbitals, dz square and dx square minus y square atomic orbitals, lie on the axis. Now, there is a noteworthy fact. The lobes of dx square minus y square and dz square atomic orbitals lie along the axis, that is, along the metal ligand direction, and their electrons are repelled by ligands to a greater extent. The lobes of dx square minus y square and dz square atomic orbitals lie along the axis, that is, along the metal ligand direction, and therefore the electrons present in these d atomic orbitals are repelled by ligands to a greater extent. This repulsion arises due to interaction between the d electron and the negative end of the ligand. Let us consider an electron present in dx square minus y square atomic orbital. This electron is repelled by the ligand to a greater extent because the lobe of atomic orbital containing this electron lies along metal ligand direction. Similarly, the electron present in dz square atomic orbital is repelled. If an electron is present in this dz square atomic orbital, this electron will be repelled by the ligand to a greater extent because here also the lobe containing the electron lies along metal ligand direction. On the other hand, the lobes of dxy, dyz and dxz atomic orbital lie in between the axes, that is away from the metal ligand direction, and their electrons are repelled by the ligands to a smaller extent. Let this be the orbital dxy. The lobes of this d atomic orbital lies in between x and y axis. The electron present in this atomic orbital is repelled by ligands to a smaller extent because the lobe containing this electron lies in between the axes, that is away from metal ligand direction. And what is the consequence of this phenomenon? The energy of dx square minus y square and dz square atomic orbitals increases to a greater extent because the electrons of these d atomic orbitals are repelled to a greater extent. The energy of dxy, dyz and dxz atomic orbitals increases to a smaller extent because their electrons are repelled by ligands to a smaller extent. And the d atomic orbitals of the CMI are split up into two sets. And this is the consequence of this electrostatic repulsion. The higher energy set of dx square minus y square and dz square atomic orbitals is called Eg set of orbitals, while the lower energy set of dxy, dyz and dxz atomic orbitals is called T2g set of orbitals. Thus, a splitting of d atomic orbitals of the CMI in an octahedral crystal field can be represented as follows. These are 1, 2, 3, 4, 5 degenerate d atomic orbitals of the free transition metal ion. But when this transition metal ion forms an octahedral complex, the energy of dx square minus y square and dz square atomic orbitals increases to a greater extent because their lobes lie on the axis, that is along metal ligand direction, and their electrons are repelled by ligands to a greater extent. On the other hand, the energy of dxy, dyz and dxz atomic orbitals, that is T2g set of orbitals, increases to a smaller extent because their lobes lie in between the axis, that is away from metal ligand direction, and their electrons are repelled by ligands to a smaller extent. And now the reality. The weighted mean of energies of T2g and Eg sets of orbitals. The weighted mean of T2G and Eg sets of orbitals is regarded as zero energy level or barycenter rather than the energy of d atomic orbitals of the free transition metal ion. The energy of free d atomic orbitals the energy of d atomic orbitals of the free transition metal ion is not regarded as the zero energy level. Instead, the weighted mean of T2G and Eg set of orbitals is regarded as zero energy level, and it is d atomic orbitals of transition metal ion in a spherically symmetrical crystal field, while these are d atomic orbitals of the transition metal ion in octahedral crystal field. Distribution of electrons between T2G and Eg set of orbitals in octahedral complex. Let us see in the previous slide. The energy difference between highest energy d atomic orbital and the lowest energy d atomic orbital is called crystal field splitting energy. Here it is denoted by delta O, not delta 0. It is delta O, which is crystal field splitting energy in octahedral complex. The T2G set of orbitals is 0.4 delta O below the zero energy level. That is, its energy is minus 0.4 delta O, while the energy of each set of orbitals is above the zero energy level by 0.6 delta O. That is, the energy of each set of orbitals is plus 0.6 delta O. And now see the distribution of electrons between T2G and Eg set of orbitals in octahedral complexes. And before it, let us discuss two terms. First term is pairing energy. The amount of energy required to pair up two electrons in the same orbital is called pairing energy, and it is denoted by P. Let us see it again. The amount of energy required to pair up two electrons in a single orbital is called pairing energy, and it is denoted by P. And the other term is crystal field splitting energy. As we have seen earlier, the difference between the highest energy d atomic orbital and the lowest energy d atomic orbital of the CMI in a complex compound is called crystal field splitting energy, and it is denoted by delta with suitable subscript such as O, T, Sp, etc. And there are now two probable cases. First case, delta O is greater than pairing energy. And an example of this type of complex compound is CONH3 triple plus. It contains NH3 as ligands, and NH3 is a moderately strong ligand. It causes greater splitting of d atomic orbitals. The splitting of d atomic orbitals depends upon various factors, and one of them is a strength of ligand. Greater the strength of ligand, greater will be the splitting of d atomic orbitals, and it is a strong ligand, and therefore delta O is 23,000 centimeter inverse, while the pairing energy is 21,000 centimeter inverse. Here, the value of delta O is greater than the value of pairing energy. CO triple plus ion contains 6 electrons in the d atomic orbitals. And when CO triple plus ion forms octahedral complex CONH3 triple plus, these 5d atomic orbitals are split up into T2G and Eg set of orbitals. This is the first electron, second, third. If the fourth electron is promoted to each set of orbitals, 23,000 centimeter inverse energy will be required, while only 21,000 centimeter inverse energy will be required to pair up the electron in this orbital. And this is why the fourth electron is paired up here, the fifth electron is paired up here, and the sixth electron is paired up here. And such complexes are called low spin octahedral complexes. The octahedral complex, in which the number of unpaired electrons is lower than that in free transition metal ion, is called low spin octahedral complex. CO triple plus ion has 4 unpaired electrons, while CONH3 whole 6 triple plus has no unpaired electrons, and hence it is a low spin octahedral complex. There is another case, delta O is a smaller than pairing energy. An example is COF6 triple minus. Here F minus is a weak ligand and it produces weaker electrostatic field around CO triple plus ion. Therefore, delta O is only 13,000 centimeter inverse, while the pairing energy is 23,000 centimeter inverse. Here delta O is smaller than pairing energy. These are d atomic orbitals of CO triple plus ion in a spherically symmetrical crystal field, and when CO triple plus ion forms an octahedral complex COF6 triple minus, these 5d atomic orbitals are split up into two sets, T2g set and EG set. This is first electron, second electron, third electron. If fourth electron is promoted to EG set of orbitals, the amount of energy required is only 13,000 centimeter inverse, while if the fourth electron is paired up here, 23,000 centimeter inverse energy will be required. And this is why the fourth electron occupies EG set of orbitals, the fifth electron occupies EG set of orbitals, and then the sixth electron is paired up in lower energy T2g set of orbitals. Thus, the electrons are filled in T2g and EG set of orbitals as if they are degenerate. The number of unpaired electrons in this complex compound is 4, which is same as in the free transition metal ion, and such complexes are called high spin octahedral complexes. The octahedral complex in which the number of unpaired electrons is same as in the free transition metal ion is called high spin octahedral complex. Crstal filled a splitting of d atomic orbitals in NiF6 2 minus. Here the oxidation state of nickel is +4. Its electronic configuration is 3d6. The value of delta O also depends upon the oxidation state of metal. Here the oxidation state of metal is +4. It attracts F minus ions towards itself to a greater extent, and therefore F minus ion exert a stronger electrostatic field around Ni4 plus ion. It causes greater splitting, and in this case delta O becomes greater than pairing energy, despite the fact that F minus ion is a weak ligand. In this case, delta O is greater than pairing energy, and therefore low spin complex will be produced. All these 6 electrons are paired up in T2g set of orbitals, and thus NiF6 2 minus is a low spin octahedral complex. Crystal field splitting of d atomic orbitals of iridium Cl6 2 minus. Here also the oxidation state of iridium is +4. Its electronic configuration is 5d5, and in this case there are two factors which cause greater splitting of d atomic orbitals. One of them is high oxidation state +4, and the another one is 5d atomic orbitals. The splitting of d atomic orbitals increases with increase in its principal quantum number, because as the principal quantum number increases, the size of d atomic orbitals also increases, and the electron present in such d atomic orbitals approach the CMI to a greater extent, and hence it causes greater splitting of d atomic orbitals, and delta O becomes larger than pairing energy. In this case, iridium 4 plus ion contains 5 valence electrons, and these electrons occupy T2g set of orbitals. Because delta O is greater than pairing energy, iridium 4 plus contains 5 unpaired electrons, while this complex ion contains only one unpaired electron, and hence it is a low spin octahedral complex. Thank you for watching the video with patience and concentration. Please like and share it. And if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.